Hello, this is Emmanuel, and in today's video, we'll be doing quiz 2. We'll be solving problems on conduction heat transfer. So we'll be solving both objectives problem and calculation problems. So please do well to subscribe to my channel. In doing that, it will motivate me to come up with more educational videos like this. So let's start. Number 1. The heat conduction equation in a medium is given in its simplest form as this equation over here. Select the wrong statement below. So for this question, this is the general heat transfer equation for one-dimensional steady state, for one dimension. So if it's for a cylinder, R is equal to R, but and n is equal to 1. So you put R equal to 1 and n equal to 1 into the general equation. After doing that, you will come up with this equation, which is similar to this equation over here, but this part of the equation is equated to 0. So they say we should select the wrong statement. The medium is of a cylindrical shape. Yes, this is true, because after putting the R equals to R and n equals to 1 of the cylinder in the equation, we obtained a similar equation like this. The thermal conductivity of the medium is constant. This is not true. This is because the thermal conductivity is in the equation. If thermal conductivity is taken to be constant, you can bring it out, then divide the whole thing. You bring it out and divide every term in the equation by the k, but in this case it's inside this bracket, so it's not constant. Heat transfer through the medium is steady. Yes, this is because the steady part of the equation, the term containing the steady part, which is Cp rho dt d small t, so change in temperature over time is equal to 0. That is for steady state processes. So that part is 0. Then there is heat generation within the medium. So E dot gen is the heat generation in the heat transfer equation. Then heat conduction through the medium is one-dimensional. Yeah, this formula is used for one-dimensional, not 2 or 3-dimensional. So question 2. The heat conduction equation in a medium is given in its simplest form as this equation. So looking at this equation, it was the sphere equation that was being used. So for the sphere, R is equal to R, then n is equal to 2. So the difference between the cylinder and the sphere is that for the cylinder, n is equal to 1, and for the sphere, n is equal to 2. So after replacing R equals to 1, then n is equals to 2 inside the general equation, you come up with an equation like this. So comparing this equation to this equation, they are very similar. So the only thing that is not in this equation is the heat generation part. So heat generation part is equal to 0. So they say we should select the wrong statement below. So the heat transfer is transient. Transient is another form of unsteady heat transfer. So here the term containing the change in temperature over change in time is present, so it's unsteady, so it's transient. This is true. Heat transfer is one-dimensional. This is true. There is no heat generation in the medium. Yeah, there is no heat generation. The E dot gen is equal to 0. Then the thermal conductivity of the medium is constant. So in this case, because the thermal conductivity is constant, we brought the k outside, then divided all the equation terms by k. So in doing that, the k will divide all the terms. Yeah. Then the last one is the medium is of cylindrical shape. This is false. So we move to question 3. A large plane wall of thickness L, thermal conductivity K, and surface area A. The left or the left surface of the wall is exposed to the ambient air, which has temperature T infinity, which with a heat transfer coefficient of H, while the right surface is insulated. The variation of temperature in the wall for steady one-dimensional heat conduction with no heat generation is what? So in this equation, you can draw a diagram to help you. So this is the material. Then one part, they said the where is it? The left part is exposed to ambient air and the right part is insulated. So this is the left part. It's exposed to ambient air of coefficients the H and of temperature this, and the right part of the material is insulated. Insulated meaning there's no heat transfer through the left part. Then so at this distance we have x equals 0, then x equals L. Then they give us the K, thermal conductivity, and the surface area. So for this question, you select a control volume. So my control volume is what I've illustrated here with the broken lines. So this is my control volume. So we'll be looking at the processes that take place, or we're observing the things that will take place in this section of the material. So at this section, air, they said ambient air is over here, and there is a material. So the mode of heat transmission is convection, and the mode of heat transfer for the material itself is what? Conduction. So taking this part, heat lost or heat transferred by conduction is equal to heat gained by or heat transfer by convection. So that's what we've written over here. So then we know, because here is insulated, there is no temperature difference between this part of the material and this part of the material. So T surface over here is equal to T surface over here. So there will be no gradient. Or there will be no thermal conduction in this part. So dx is equal to 0. So that is what is over here. dx was equal to 0, then it's equal to the convection part. Then you make T surface. So you come and get T surface is equal to T infinity, which is the ambient temperature. And we know T surface is the temperature at the beginning. So T surface is Tx when x was 0. So T surface is equal to T infinity. So for this question, the answer is E. Then we'll go to question 4. So in question 4, a solar heat flux Q.S is incident on a sidewalk whose thermal conductivity is K. Solar absorptivity is this over here, this sign over here, alpha S, and the convective heat transfer coefficient is H. Taking the positive direction X to be towards the sky and disregarding radiation exchange with the environment surface, the correct boundary condition for this sidewalk surface is. So in this question, total heat absorbed plus heat transfer by conduction is equal to heat transfer by convection. So you put heat transfer absorbed, that's the absorptivity multiplied by the heat flux, plus heat transferred by conduction, which is equal to heat transferred by convection. So this is the equation that you get. So looking at the option, the best solution is the C. So the answer is C. So let's move to question 5. A plane wall of thickness L is subjected to convection at both surface with ambient temperature T infinity 1 and heat transfer coefficient H1 at inner surface and corresponding T infinity 2 and H2 value at the outer surface. Taking the positive direction of x to be from the inner surface to the outer surface, the correct expression for the convection boundary is, so this one too, with the aid of a diagram, that's what you write. So air is over here and air is over here. T infinity 1 is the temperature of the air, H1 is the coefficient, and the temperature of the air over here and the coefficient, and this distance is at distance 0 and this distance is at distance L. So taking the control volume over here, heat transfer by convection is equal to heat transfer by conduction. So this will be the formula. Then the temperature over here is 0. So Tx is T0 minus T infinity 1 over here. Then the temperature at this point too is T0. So that's why we use T0 over there. So the correct answer will be the A. So let's move to question 6. Consider steady one-dimensional heat conduction through a plane wall, a cylindrical shell and a spherical shell of uniform thickness with constant thermophysical properties and no thermal energy generation. The geometry in which the variation of temperature in the direction of heat transfer will be linear is, for this one, is the plane wall A. Because, example, this is a plane wall. The temperature gradient over here will be that of a straight line. The slope will be of a straight line. So the answer is A. Then we move to number 7. The conduction equation boundary condition for a diabatic surface with direction n being normal to the surface is, so this year they gave a clue. They said adiabatic surface. So adiabatic surface temperature is constant. So if temperature is constant, so there is no temperature, there is no change in temperature. So dt dn, which is a direction, is equal to 0. So the temperature gradient is equal to 0. So this answer is B. Then we move to question 8. So in question 8, they said the variation of temperature in a plane wall is determined to be Tx is equal to 52 multiplied by x plus 25, where x is in meters and T is in degrees Celsius. If the temperature at one surface is 38 degrees Celsius, the thickness of the wall is what? So in this equation, they've given you the variation of temperature. So it is the variation of temperature. So, and they are saying the temperature is 38. So if the temperature is 38, what is the thickness? What is the x? What is the x? So you make x the subject, you come and get 0.25. So the answer is 0.25, which is C. Then in question 9, the variation of temperature in a plane wall is determined to be this, where x is in meters and temperature is in degrees Celsius. If the thickness of the wall is 0.75 meters, the temperature difference between the inner and outer surface of the wall is what? So in this case, they are talking about temperature difference. So we cannot solve it the same way as we solved in number 8. Number 80, this over here is temperature. So we want temperature difference. How do we get temperature difference? You have to get dt. So you integrate this term over here. You differentiate this term over here. So dt dx is equal to what? Negative 60. Then you make dt the subject. So dt, which is the same as change in temperature, is equal to negative 60 plus the x. And they gave you the x, which is the change in distance or the thickness. So negative 60 times 0.75 is equal to 45 degrees Celsius, which is B. So the answer for question 9 is B. So let's go to number 10. So in number 10, the temperature difference, the temperatures at the inner and outer surface of a 15 centimeter thick plain wall are measured to be 40 and 28 degrees Celsius respectively. The expression for steady one-dimensional variation of temperature in the wall is what? So this is an illustration of what is over here. So temperature here is 40 and temperature here is 28. Then at this distance we have x equal to 0, and at this distance we have x is equal to 15. So they are telling us to find the variation in temperature equation. So we know for steady one-dimensional variation of temperatures in a wall, we use this equation. This equation was derived from the general equation. So for plain wall, and then R is equal to X and N is equal to 1. So you put this in the general equation. Then because it's steady, the small t per change in temperature over time is 0. So that part will go to 0. Then the heat generation part to E dot gen will be equal to 0. So it will be left with this equation over here. So you will integrate this equation. So after integrating this equation, you get a constant C1. Then you integrate it again. So you integrate it again. So after integrating it again, you come and get C1x plus C2. So after getting this equation, linear equation over here, you have to find your C1 and C2. So we use boundary conditions. To find that. So at x equals 0, the temperature is what? 40. And at x equals 15, the temperature is what? 28. So you use the boundary conditions. So for the first one, at x equals 0, you put 0 over here, you multiply the C1 by 0 plus C2 is equal to 40. So you come and get C2 is equal to 40. So after getting C2 is equal to 40, you use the second boundary condition. So at x is equal to 15 is the temperature was equal to 28. So now you make C1 the subject, then you come and get negative 80. Then you put the constant C1 and C2 into the equation, this one that we got. Then you get this answer, which is D. The answer for number 10 is D. Then you come to number 11. The thermal conductivity